In this video, we'll review the power and sum rules for derivatives. The goals of this video will be to cover the building blocks of derivative rules. We'll also talk about the applications of the derivative in business and economics. In what follows, we'll assume that f and g are differentiable functions of x. The first rule is the constant multiple rule that says that if you take the derivative with respect to x of f, where f is multiplied by a constant k, then the derivative is k times the derivative of f prime. This just says that you can take a constant multiple out of the derivative. If you're taking the derivative of a sum or difference of differentiable functions, such as f and g, then you take the derivative of them separately. So the derivative of f plus g is f prime plus g prime, and the derivative of f minus g is f prime minus g prime. The power rule says that if you take the derivative of a function raised to an integer or non-integer power, then you multiply by the power and subtract the power by 1. For instance, if I have the function x squared and I want to take the derivative, then I lower the power and subtract 1 from the previous power so that the derivative of x squared is 2 times x to the first. We don't write 1 typically, so it would just be 2x. Special cases of this property would be the derivative of a constant is 0. That would be because I could write this as k times x to the 0 power, and the derivative would be k times 0 x to the 0 minus 1, which we know anything times 0 is 0. And the derivative of x, which is x to the first, is 1 times x to the 0. Anything to the 0 power is 1, and so the derivative of x is just 1. The derivative of an exponential function, e to the x, is just e to the x, but the derivative of any other base, such as a to the x, is a to the x times the natural log of the base a. Finally, the derivative of the natural log of x is 1 over x. We're going to put all these together for the following practice problem. If f of x is negative 8 times the square root of x plus 6 times x to the fourth, we'll want to use the power rule and the sum and difference rule to take the derivative of this function. So we'll want to rewrite any radicals with their fractional exponents, and any functions that are in the denominator we'll write with negative powers. So we can rewrite f of x as negative 8 times x to the 1/2 plus 6 times x to the negative fourth. Then f prime of x is negative 8 times 1/2 times x to the 1/2 minus 1 using the power rule, plus 6 times negative 4 times x to the negative 4 minus 1, and that's using both the sum rule as well as the power rule. The rest of the work will be to simplify this expression and get it back to its original form. So we have negative 4 x to the negative 1/2 minus 24x to the negative 5. Any negative powers need to be put into positive by moving them to the denominator, and any fractional exponents need to be made into radicals. And so f prime of x is negative 4 over the square root of x minus 24 over x to the fifth. Taking a look at part B, we want to take the derivative of g of x, which is 6 times e to the x minus 7 times the natural log of x. G prime of x, the constant 6 would come out of the derivative, and we're just looking at 6e to the x minus 7 times 1 over x, which we can clean up to write 6e to the x minus 7 over x. Where does y equal x squared minus 10x plus 3 have horizontal tangents? We want to find the equation of the tangent line to y when x equals negative 2. So remember, a graph has horizontal tangents when the slopes of the tangents equal 0, and then we find the slope of the tangent by taking the derivative of the function. So we'll start by taking y prime using power rule and the sum and difference rule. So we end up with 2x minus 10. And then where it has horizontal tangents is where it equals 0. So 2x minus 10 equals 0. And then x would equal 5. So y equals x squared minus 10x plus 3 has a horizontal tangent when x equals 5. We can actually find the point by plugging 5 back into the original function. So it has a horizontal tangent at 5, negative 22. We want to find the equation of the tangent line to y when x equals negative 2. And so this time we'll take our derivative y prime equals 2x minus 10. We'll find the slope of the tangent line when x equals negative 2 by plugging negative 2 into the derivative. So the slope of the tangent line at x equals -2 is -14. We also need the y value to plug into our point slope form as we did in the previous video from section 2.2. So we'll plug in -2 into our function, the original function. So we will be using the point -227 with a slope of -14. The equation of the tangent line is -14x minus 1. Now we'll look at the applications of the derivative in business and economics by looking at a few definitions of terms that we'll see throughout the rest of the semester. Your cost is the money you have to spend to produce your items. The fixed cost is the amount of money you have to spend regardless of how many items you produce. Fixed costs can include things like rent, purchase cost of machinery, and salaries for office staff. You have to pay the fixed cost even if you don't produce anything. The total variable cost for Q items is the amount of money you spend to actually produce them. Total variable costs include things like the materials you use, the electricity to run the machinery, gasoline for your delivery vans, maybe the wages of your production workers. These costs will vary according to how many items you produce. The total cost for Q items is the total cost of producing them. It's the sum of fixed costs and total variable costs for producing Q items. So we could say that total cost is equal to our fixed cost plus our total variable cost, which oftentimes is reflected as a linear function. Fixed cost would relate to your y-intercept, and the total variable cost would have a slope attached to it, multiplied by your input variable, often used as Q. In the previous video, we talked about the word marginal, implying that we're discussing a rate of change, and we would be wanting to find the derivative of producing one additional item after producing Q items. So marginal cost at Q items is the cost of producing the next item. So that's the total cost of Q plus 1 items minus the total cost of Q items. In many cases, though, it's easier to approximate this difference using calculus. That would be if your total cost is not a linear function. It would be a lot easier to use calculus. Some sources define the marginal cost directly as the derivative, which would be the derivative of the total cost function. In this course, we'll be using both definitions interchangeably. The units on marginal cost will be cost per item. It costs the square root of x dollars to produce x golf balls. What is the marginal production cost to make a golf ball? What is the marginal production cost when x equals 25 and when x equals 100? So the first question is just x, golf balls. Then we want to evaluate our derivative at 25 and 100, and we want to make sure to include units. So marginal cost is the rate of change of the cost function, and so marginal cost of x golf balls is going to be c prime of x, which will be the derivative of your square root of x function. And we'll want to use the power rule here. So we'll write x to the 1/2. That's going to be 1/2 times x to the 1/2 minus 1, or 1/2 times the square root of x. This will be your marginal cost of x golf balls. So this will be the dollar per golf balls. So what is the marginal cost, production cost when x equals 25? We will be plugging in 25 in for x, or 1/2 times the square root of 25, or 1/2 times 5, or 1/10, which will be 10 cents per golf ball. So it's 10 cents additional per golf ball when producing 25 golf balls. We can do the same thing for the 100. So 1/2 times the square root of 100, which would be 5 cents per golf ball. That would be the marginal cost when producing 100 golf balls. It'll cost 5 cents more per golf ball. So what it looks like is the more you produce, the lower your cost would be per golf ball. These are things you want to take into consideration when you're deciding how many units to produce. Demand is the functional relationship between the price P and the quantity Q that can be sold, that is demanded. Depending on your situation, you might think of P as a function of Q or Q as a function of P. Your revenue is the amount of money you actually take in from selling your products, And so revenue is price times quantity. And if we're using our P and Q variables, which often you'll see in the textbook, that would just be P times Q. That would be your revenue. Total revenue for Q items is the total amount of money you make for selling Q items. Marginal revenue, again, is the cost of producing the next item. So that would be your total revenue at Q plus 1 items minus your total revenue at Q items. And just like with marginal cost, we can use the definition that marginal revenue is the derivative of total revenue. The profit is what's left over from total revenue after costs have been subtracted. So profit can be found by taking total revenue and subtracting total cost. The average profit for Q items is profit over the number of items produced, and then marginal profit is just the derivative of your profit function. Here are the graphs for total revenue and total cost for producing and selling a certain item. The horizontal axis is the number of items in thousands. That's your Q axis. The vertical axis is the number of dollars, also in thousands. First, notice how to find the fixed cost and variable cost from the graph. Here, fixed cost is the y-intercept of the total cost graph. That is when T of C is evaluated at 0. The graph of the total variable cost would have the same shape as the graph of total cost, shifted down. So total variable cost is total cost minus fixed cost. The marginal cost is the slope of the tangent line to the total cost curve. The marginal revenue is the slope of the tangent line to the total revenue curve. Profit is the distance between total revenue and total cost curves. So our profit would be this area here. The biggest profit occurs exactly when the tangent lines to total revenue and total cost curves are parallel. This is the rule: profit is maximized when marginal revenue equals marginal cost, which will be explored later in this chapter. A company produces very unusual CDs for which the variable cost is $12 per CD and the fixed costs are $40,000. Assume that they will sell all the CDs they can produce and their selling price is $60 each. Let X be the number of CDs produced. Write the total cost, total revenue, total profit, marginal profit as a function of the number of CDs produced. So let's start with our total cost. Remember, total cost is the total variable cost plus your fixed cost. So the variable cost is $12 per CD, where X represents the number of CDs. So that's 12X for your total variable cost plus your fixed cost of $40,000. Your revenue is going to be how much you sell the items for times the number of items sold. Your profit is going to be your revenue minus cost. So that's 60X minus 12X plus 40,000. Should make sense that our profit will be negative our fixed cost because we're not making that money, we're paying that money just initially to get our business off the ground. Finally, our marginal profit is going to be the derivative of our profit function, which is 48, if we use the constant multiple rule and the power rule. In the next section, we'll discuss more derivative rules, this time for products and quotients.